LMS controller to update the weights of the filter, generate the control action to counterbalance the effect of the external disturbance. Okay? I just want to say one very important thing. For example, if this is a structure, and this structure, for example, it is sitting on a shaker. On this system, if I want to implement the feed forward, I'll come on this end and measure X as the reference input. And for example, if this is like a platform or any structure that has, for example, one location where it's very critical. So for example here, then I'll put my sensor here for measuring the error signal. So this is my error signal. And this is my reference input. These can be, for example, accelerometers and so on and so forth. I will show you. You have to be very careful when you pick up these. Now when I run this algorithm, this is a shaker that's exciting this beam or this structure. Now, for example, because of this setting, it will move very large at the first mode of vibration. So this will be like this. Because of this fact, this sensor will measure very large signal. Now I take this along with the disturbance, that a measure of a disturbance, and then between these two I put them in the LMS. What it does, tries to minimize the error signal. So what would it do? It would be like this. So this is before the control. And then this is after the control. Hopefully, if it minimizes it to 0, that's fine. But the bottom line is, the structure is not free of vibration. The structure is free of vibration here only, where I have the error signal. If I want to quiet the structure in other places, I put more sensors in other places. And then I use multi-input, multi-output LMS. But I will quiet the structure only at the error sensor location. This we have to keep it clear in our heads. The LMS, not like other algorithms, like for example when we said velocity feedback, it meant everything will drop. Everything will drop. Here, it will drop only where I have my error signal. So this is very important to keep in head. So this is the source of excitation. And I am recording a measure of this excitation. In this diagram, if you look at X and D, these two are correlated. These two are exactly correlated. For example, D is the unbalance that I generate in the shaker. The unbalance, this is a force that I generate. A measure of this force is X, which may be accelerometer, or in many shakers they have a head that has impedance head, that has velocity or force or combination of these two. So I can use this as measure of the reference input. These two signals are related. So for example, if I have a column in wind loading, the wind loading will make this column oscillate by vortex shedding. And if you look at the antenna of your car, or some cars, the old cars now, the new cars don't have antenna. So the old cars, they have antenna with a spiral on the antenna to break the vortex shedding. But anyway, if I don't have the spiral, the antenna will oscillate. I can measure the oscillation, but I can also measure how is the wind loading on this. For example, I can put load sensor on this. So this will be measure of the loading. I want to minimize the vibration, so I have to measure the deflection. Between these two, I can implement an LMS control. So you have to use some imagination to get indication of where the disturbance can be monitored. And this is the final result. We don't want to mix between these two. This is the source, and that's the result. So the input reference is the source of generating the vibration. And then the amplitude of vibration is the result of this excitation. So now for this system, we will implement the LMS with the finite impulse response filter. And we said, I will generate control action Y is equal to the error signal E. I'm sorry, the error signal E. Is equal to Y plus the disturbance. Y I will generate it from this filter. And this filter will have summation W, and then we give this coupled subscript. The weights in every station multiplied times the X, and then this X is at sample order K delayed by the order of the filter location. So this is K is the sample order, and I is the delay that I introduce in the FIR filter. And then we'll make from 0 to whatever number that you want. I think last time we called it capital. And then here, D. Now I'll define performance index for this system is the error squared. Then the objective function or the performance index is the error squared, and the W's here are the weight of filter station I. So now we update the weights in order to, or such that F is minimized. And we said now we'll have W station I at k plus 1 equal to wi at the previous sample, time sample k, and then we'll move in the negative direction of the performance index, which is the steepest descent, a distance mu times the gradient of this function let me just write it instead of the gradient, just will write it directly, partial f by partial wi, and this is all taken at sample k. And from here, and from the last equation, then partial f by partial wi will equal to the error e, partial e by partial wi. And from this equation, the d is independent of the weight. So when I take the partial derivative of this at station I, so it will be just this number xk I. So this will equal to 2e x k minus I. And now I substitute here. I have wi k plus 1 is equal to wi k minus 2 mu e x k minus I. And the whole idea is, of course, 2 mu, I can call it another name, mu bar, for example. Minus I. And because this is a time sequence at sample k plus 1 and sample k, I can put this in the z domain. And in the z domain, I can factor out the same as we've done with the time derivative. So this will be z wi of z, and the here will be wi of z minus mu bar, and then I'm going to combine all these in one term, and we call this last time small q of I, and when I take the z transform of it, it becomes cap q of I. And then I can extract the wi now in terms of qi. Wi of z will equal to minus mu bar z minus 1 q bar. And from here, we came up with this drawing. This is the reference input. Again, the error signal, the disturbance. Now I go in this box, which is the LMS controller. The LMS controller has two inputs. To generate the Q, I have the error E, and then the reference input, I have delay, depending on how many filter elements I have. So I have delays on the X, and then I multiply it times the error to generate the Q. Multiply it times 2 mu over z minus I to generate the weight change. The weight change times the delayed response, I add them to the error. The weight change times the delay response from all stations, I sum over the n, and then add to disturbance. Okay, now all this we will replace it with one box, which is a box in MATLAB. Okay, so now the result of all this. I put here the inputs. I put here the error signal. And then I generate from here the output. And if I want, I can also generate the weights. So MATLAB, this is LMS. The input is my X. The error is my E. The output of this is my Y. And then here is the weights. This is Simulink. Okay, I just want to show you, after you make the worksheet that you want to work with, then you come here. Of course, there are many control toolboxes, and then one that we need is the DSP, the Digital Signal Processing Toolbox. And then it has many sub-blocks. The menu, the pull-down menu has many things. One of them is filtering. I go in filtering, and then it has adaptive filters, filter design, filter, and so on. We need the adaptive filter. Adaptive filter has, this is horrible, isn't it? Kalman adaptive filter, LMS, and then FLS, another type filter. So now I'm going to take this and put it in my menu. Okay? So in my work pad. And if you look at this box, let's make this bigger now. Then I can take this. So if you look here, this is the input, and then the error signal, and then the output, and then the tabs, which are the W's. Now if I double click on this, you will see the following. The filter length, how many stations we need. So the N, how many taps or how many delays we have. And then here is the step size, which is the learning rate, mu. The learning rate, mu. And then the last value is the initial value for the weights. So you can begin from any weights that you want. The easiest one is just put 0 for all the weights. So we'll select the number of filter stations, N, and then the step size, which is the learning rate, mu. And then once you're done from this, then you just connect it to the remaining part of the circuit. Very similar to the diagram that you have now with you. So now I'll go back to, I'm going to remove this. This is the diagram that you have now. And here there are several very important things. Let me just turn on the lights first. Come in hand, please. We'll switch again, put the projector. I'll put here my structure. But because everything that I'm doing is in steps, discrete time steps, so I have to put my model in the discrete state space. Okay? What is the discrete state space? We have the continuous time domain. Looks like this: x dot is equal to ax plus bu, and for example I have y is equal to cx. I want to convert this to discrete time domain. Also state space. So one very easy way of doing this is to say x dot. I can generate this x dot from x at sample k plus 1 minus x at sample k. So that's the difference divided by the distance on the time domain corresponding to dt. So this is dx, and I divide by dt. dt is the spacing between two consecutive samples, which is the sample interval. So if your controller samples at 5 kilohertz, then this sample interval will be 1 over 5,000. Okay? Depending on how fast your controller is. Now, I can replace this here. So when I do this here, this becomes x k plus 1. And I'll take this to the other side, and I'll multiply t by the two sides. So this will equal to x of k plus a t Now this equation will stay the same whether you have continuous time domain or discrete time domain, because whatever I measure, I'm going to select only 1 or 2 or 3 states. The rest I cannot measure them. So if I measure x velocity or position now, then this means that's what I have available for me now. So the same equation will hold for discrete time domain, but we can make it cleaner by saying y at any sample k will equal to c times k. So now from here, I'm going to erase this equation because I don't need it. This is very similar to the continuous domain. Okay. Now, if you look, I have xk plus 1, I have xk twice, so I'll factor it out, and this will be identity dnu. Now this and this, I can group them and rewrite this equation like this: xk plus 1, and here is x of k, u, and this will be my a discrete, and this will be my b discrete. So for continuous time domain, I have the description. So if you write finite element and you generate the K and M matrix and you generate the state space equation, I can automatically go from here to here very fast. Take this A, multiply it times the sample interval and add to it I. Take this B, multiply it times the sample interval. Then you generate your discrete system model. I need this to go into the implementation of the LMS, because the LMS takes discrete samples. So now this is my model. Here I put two matrices so I can select one time position sensor, one time velocity sensor. So you can see why I'm doing this. Okay. The output, I'm going to make the output always the position of the system. And I'm going to put it on a scope. The signal from the output of the system, which I am using as an error signal, I take it and feed it to the LMS block from the DSP toolbox. I'm going to feed it here through this box. This box is called zero order hold. Again, the output from here is output. I don't need this anymore. The output at this point will look like this. For example, it is, if I am measuring the position, then this would be the position x, for example, at sample k. This is position at sample k plus 1, and so on. X, k plus 2. But I don't feed this to the LMS, because if I feed it to the LMS block, then I have this and I have nothing in between. I have this and I have nothing in between. The signal disappears. Now, in any system that you have analog to digital converter, what it does is like this. it takes this signal and hold it constant at the output. Until the signal comes, it measures it, and then he holds it constant. And the same thing now, this third signal comes, and then he holds it constant, and so on. So now, in effect, I am making the analog signal stepped signal, and I am maintaining it constant throughout this period, which is this sample interval t. If I do it like this, like all 99% of the analog to digital controller, this is called zero order hold. If I make it Simpson linear, then it is first order hold, and so on. But this is the most common type. Now, this signal that's coming out from the system, I'm sampling it, and I am holding it constant steps, and I am sending it as an error signal to the LMS block. The same thing for the disturbance. The disturbance, I am using it in two locations here. I'm using it as disturbance, and at the same time I'm using it as my reference signal, X. So this is D, and this is X. So now, this signal, I'm going to chop it again and make it zero order hold signal. Now the output from this box will be discrete samples. I'm going to zero order it and hold it again. Now once we get the computer going, it will go into this block, and you see what do we have to put in. The main thing we have to put in is the sample time. So he knows how long to hold this signal constant. Okay, now I have disturbance going into the system. I correct the disturbance by feeding back the output through negative feedback. This doesn't matter. You know, if you put 1 or you put -1, it doesn't matter, because it will correct by itself. Because this is adaptive control, tries to minimize this output. It tries to minimize the output that's coming, the error signal. So if the error goes high, it will try to adjust the weights, and instead of W, it will put -W. It will try to minimize the error square by adjusting the weight. So if you put plus or minus, it should work. Okay. Now we take this number and feed it back, and then input to the system. Okay. And I can also look at this channel, which is the output, which is this number, Y, which is the control effort, how much I put as a controller, and so on. Okay. Now, in this block, I'm going to use very simple spring mass system with damper, which is the system that we used before. So I'm going to use x dot is equal to 0, 1, minus 1, minus 1, and then x plus 0, 1, and u. And then y is equal to c and x. This c, I will vary it in front of you so you can see what will happen. So I put this system, A and B, and for digital equivalent, I'll generate from them A sub D and B sub D. For this system, this has the differential equation, x double dot plus x dot equal to u. And if we forget the damping then this has natural frequency 1. The undamped natural frequency is equal to 1 radians per second. This is a single degree of freedom system.
So the adaptive filter and the discrete state space have different sampling rates or something? Is that why?
Yeah. For example, here, if we go on any one of these, then it says what is the sample time. Because my frequency is 1, I'm sampling every 100, every 10 milliseconds. So this is plenty, 1 over 100. If the frequency is high, then you take the rule of thumb, take the highest frequency and divide it by 100. So you can have enough data. So this is for the zero order hold for all of them. Now let's look at this block. This block, the first line is A, which is discrete. So now it is equal to identity plus the A matrix that we have on the last board times the sample interval. Identity I2 plus this matrix 0, 1, minus 1, minus 1 times sample interval T, which is 0.01. The B is equal to 0.01 times 0 and 1 transpose. The C, I took C here as identity matrix. And then the D, then the initial conditions, and then the sample rate. And then the sample rate. So the system description in the discrete time domain, you put the A, B, C, D, and then the sample time. Okay? Now we finish from this, the system description. Here, I'm not going to begin with this. I'm going to begin first with position. So in this location, I have the position as my output sensor. And then I am sending it as an error signal to the LMS channel. Here, it will be the position. Always the position. Okay, 1 and 0. Okay. Now, here, this is the excitation. Function generator generates. The function generator, I generate sine wave. Amplitude of 1, and then I adjusted the frequency, and then we have the units here, radians per second or hertz. So I'm going to begin first by, this is 1. And 1, because I'm hitting this resonance, okay? And you will see I'm using it for another purpose also. Now we're ready, we can simulate what we have. And then we go in the simulation. and started the simulation. We're done. I look at the output. This is my output. Okay. So there is little decay. Let me see first the learning rate here. We have 0.001, and also here in the filter that I used two stations, because this is a second order system, so the maximum I need is 2, but you can put as many as you want. And then this is my step size, my initial conditions. Okay, now let's take this. I'll leave this for 1 second, and then let me take this. And instead of 1, I'm going to make this 2, the frequency. And then run the same program. We're done. I'm going to look here. And you see the result here? It's going unstable. It's going unstable. The first case was slowly decreasing, but very slowly decreasing. At the second frequency of 2, it increases. Okay? I'm just see this, and then I'll summarize them. And then now I'm going to take here, and instead of position sensing, I'm going to take 0 and 1, which is velocity sensing. And now we'll run the two cases. Again, at 1 hertz, let's do the 1 hertz first. With 1 hertz, it drops. Okay? So this is now learning. And if I keep this time going, then eventually it would go to 0 with the right weights, then we are okay. We can control this. Now we'll go to make it 2, and then run again the simulation. And again, in this case, it is dropping. Again, in this case, it's dropping. Now, the summary of all this. I used the position as my error signal. And then I did them at 1 radians per second and 2 radians per second. When I use this, I'll see the error is decreasing but slowly. When I used at 2 hertz, the error increasing. Now here, the error was decreasing. This was decreasing. This is time, 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 and time. Now, just to look at what these magic numbers that I used, I'm going to plot here the frequency and the amplitude, which is the output of the system, which is the error. And then I'm going to plot here phase angle. For this system, it has resonance at 1. So it will have something like this. Now if I go here and plot the phase angle, you will see the phase angle for low frequency, which is close to 0, will be 0. If I don't have any damping. And when I get to 90 degree, then this will drop. And then if I move higher than 1, then this will go to 180. If I have damping like this system, then we'll have something like this. Have something like this. So the important thing now, if I use position sensor, I have phase shift at 1 Hertz of 90 degree. When I go to 2 Hertz, the phase shift becomes almost 180 degree. So if it works in one direction, at this point, it will work. If I try to make it work in this direction and I have negative, almost 180 degree on the opposite direction, so it will not work, because I'm using this position sensor. The phase angle becomes very, very important. Now when I use the velocity sensor, we go back to the first lectures, I make the system interlaced, poles and zeros. So the system will have maximum phase shift of 90 degree, plus and minus 90 degree. So let me go back again and make this velocity. So now again the system was x double dot, x dot is equal to u, and from here I can write down x is equal to 1 over s squared and u, and for this system I can plot the phase angle like what we have here. And for this system, I am adding a derivative in the numerator. So this derivative will have phase angle between 0 and 90. This is between 0 and 180. So I can cancel the 90 in the numerator with 90 in the denominator. So I have plus 90 and maximum minus 90 here. So I'm bounding the phase shift between plus and minus 90. Here it is between 0, 180 degree phase. Here between plus and minus 90. And the bottom line of LMS to work without changing the sign. Now I'm going to change the sign and you will see it will work at 2 Hertz. At 1 Hertz I have to change the sign to make it plus and or minus. If I flip this sign, it will work. But of course you don't want to have a controller that will flip the sign depending on the excitation frequency, because you don't know what's the excitation frequency. So you want your controller to stay as it is to work for any frequency range. To guarantee this, you have to make the phase angle of the system between plus and minus 90 degrees. And when you do this, then this is called the plus and minus degree rule of thumb. If I cannot guarantee this, then we have to do something else. Okay? And we will prove this, and then we'll show you also what we have to do. See the time first. Let me just go back again here. I'm going to go back to position. And we'll look at the case which did not work, which is at 2 Hertz. Okay, if this is the 2 Hertz, and then I'm going to run it as it is. This is the output which is diverging. Now I come here and I'm going to change this sign. So it starts converging. Okay? So if you want to make this controller work, you have to sit down next to it and adjust it depending on the frequency. And of course this is unacceptable. So if you want to have a controller that will work without worrying about these changes, then you have to maintain the phase angle between plus and minus 90 degree. Now, what else I wanted to show you? Of course we can see here the shape of the control effort, and control effort will increase. Of course, if you have enough time, then you train the system as it moves. It will try to cancel completely the system error. Once you have this, then you have the right weights. You can use this to do your controller without changing the weights. The nice thing here, if you have any changes in the excitation, then the system adapts to it by adjusting the weights, so you can get the new weights that can cancel the input. Okay. Use Bode diagram. Here just a little so this has a numerator is equal to 1, denominator is equal to 1, 1, and 1. And then apply certain frequency is equal to log space minus 1 to 2 and W. I'm sorry. Let's say 100 points. And then do this command, magnitude and phase angle, N, D, and W. So check the phase angle of this system and of this system. So this will have numerator is equal to 1 and 0, and the same denominator. And then repeat the same things. So get the MA1, phase 1, make this N1, D1, now you will see that the phase angle here is between 0 and 180, and then here it will be between plus or minus 90 degrees. Just a little thing here, the LMS, this was developed by Bernard Woodrow, and he's at Stanford University. And this is also the origin of neural network. The network is nothing but some of these filters. The filters are all linear filters. All of them linear, because I can write the equation, the output is equal to the weights times x. I can write it in a linear form. The neural network has the same thing but non-linear. And developed by AI is also origin of the neural network, which is a non-linear version of the LMS. What you've seen in the diagrams that we were plotting, this is the learning of the filter. I'm making the filter learn the system equation. For the neural network, instead of learning, it's called the training. I'm going to train the network to learn some outputs. And we can make this network take the inverse of the system, for example, or take the system. So if I want to identify the system, I make the network learn the system. Or if I want to cancel the output, I make the network reciprocal of the system. The very simple thing is, if I have a system like this is my structure. This is the simplest neural network form controller. This is my reference, and then this is my output. My objective is to make this the same like this. To make the two the same. So now I'm going to put here network that will learn how to make this matching between the input and output. Okay, so I'm going to have here take the error and then adjust the weights inside this box. Okay, If this has transfer function G, I'm going to make this train until it becomes G inverse. So when I multiply G inverse times G, it is identity matrix. Whatever I send here is exactly like what I'll get out from here. So that's the very simple neural network. This will be, it's called the inverse dynamics of the system. This is the dynamics, this is the inverse dynamics. Okay, so this will be very similar to the LMS, and it has a box also in MATLAB. And the nice thing about the neural network is that it is nonlinear. So I can make it with very small number of elements, make a real complicated system be controlled or identified by a very small network. Okay? Anyway, which is the nonlinear version of the LMS. LMS is also called the linear combiner. And the word comes from here. Because Y was the summation W and X, I, K minus I, and K. So I'm combining weights and reference input linearly, linear multiplication to generate my control action. The neural network will take the product and then apply it to nonlinear function called the activation function. We'll describe this later on. But anyway, the basis of this is the LMS controller. LMS controller. Okay. I'm not going to describe the filtered X because we have a few minutes, and I'll just say a couple words. On Wednesday, $11:28, we'll have open book and open covered again finite element method and static condensation. The optimum control, LQR, LQG, LQG, and H infinity, I guess both was full, and the output feedback. Okay, and then we just started now the LMS. And we'll have one problem from here and one problem from here. Is that fair? Okay. And it will be very easy compared to what we did last time, huh? And I'll be here, so have a good evening, and we'll see you on Wednesday. And this is our controller. And And the result is a signal that goes into our system, okay? And this method, we said, we use it when we don't need any model of the system. So this is non-model based method. Okay. What I showed last lecture, I showed this example done for spring mesh system. And we took a spring mesh system. And then this has disturbance acting on it. And then this system has this dynamics. And the dynamics has magnitude. And this is frequency. And then it has phase angle. Like this. And I took a couple runs. One run, for example, here. And one run someplace here. So this is frequency 1 and frequency 2. For second order systems, this is 0, this is minus 90, and then this is minus 180 phase angle. And I did the simulation of this LMS in 2 ways. We took error signal, either position or velocity. Okay, and then I looked at the frequency omega 1 and omega 2. When we take a position, then we've seen that the oscillation, I can train the system by adjusting these weights and bring everything down. Okay, so this converges, and then I end up with vibration is equal to 0. So this is my error signal, and then this is time. Now, if I take the same setting that I have and then run it now at frequency omega 2 here, then we'll see the following. We start from some initial disturbance. This everything is running on a continuous persistent excitation. So the excitation now is like this. And then when I turn my controller on, instead of bringing it down, then this will start diverging and the system becomes unstable. Now if I use velocity as a sensor signal, as my error signal, then these two will look like this. And I showed you this in Simulink. The main reason is for the position signal, the phase angle varies from 0 to minus 180. Or this is, like if I add to 360 degree to this, so this becomes plus or minus 90 degree. Plus or minus 90 degrees. So the phase angle here, phi, is spans the range 180 degree. So let's say between greater than minus 180 and then to 0. For this range, I am in phase. For this range, I am out of phase. Now when I come and put velocity sensor, I add to this 90 degrees. I add to this 90 degrees. So instead of plus and minus from 0 to minus 180, if I add 90 degrees to this, it becomes from minus 90 to plus 90. And the conclusion of all this is as follows. LMS works, which means makes the system stable or eliminates vibration only if the phase angle of the system is bounded between these two limits. And this is called okay. I want to redraw this drawing again here. This is my error signal. This is my reference input. Between these two, I generate the LMS controller, adjust the weight of the filter. The filter will give me an output. I'll send this output to the actuator. And the actuator will work on my system. Now here, I'm taking the system as transfer function of 1. So I'm sending the signal here from the actuator to my system, and then the output, my Y1. In other words, I'm taking the system dynamics as if they don't change the actuator signal. There is no time delay between whatever I send from the actuator and whatever the system response happened. Why? I'm assuming that I'm in this range. Okay? Everything is nice and clean. If I am in this range, it will work if I reverse the sign. But if I reverse the sign and then now I train the system and make it work here, it will be unstable here. Okay? It will work because in this range, the system does not change the dynamics. Here does not change the dynamics. So I'm taking everything as if it is, you just whatever you put now, you will see it immediately now. Okay? Now we'll show why this will work and what conditions under which this will work. But the first thing that you will try in any situation, just try it blindly, and the adjustment of the weights here, we said, this will adjust the weights in any station of the filter by updating the old weights and moving along the negative direction of the gradient some distance mu, which is my learning rate. So for any system, don't worry about the system dynamics. Take the actuator, apply it on the system. If the response goes unstable, then you just reduce this. You reduce this, you reduce it, and if you just keep reducing and nothing works, this means we are in trouble. Okay? So this will not work anymore. So we have to now do something else to ensure that this rule will apply. But blindly, the first thing is run the LMS and then start with a small rate, increase it, or if you start for a large rate, because we don't know what this rate is. In some range will be maybe 10 to the minus 6. Some application might be 10 to the plus 6. So we begin with some number, and then once you saturate the maximum voltage that you can apply to the actuator, you cannot get any more benefits. So if it doesn't work and becomes unstable, just decrease it, decrease it, decrease it. If it doesn't work, then we have to do another algorithm which is called the filtered FXLMS. Okay. And maybe around 6 o'clock we'll take you to the lab so you can see this in operation, so you can see how this will work. So now the filter FXLMS. Again, this is my FIR filter. And then now here my plant is no longer one in dynamics, but it has some transfer function, C. And then instead of Y1, I'm going to call this Y2, because Y1 that we have in this diagram will be here. And then we have the error and the disturbance. And then now here we have the LMS as it is. And then here we have the reference input. And then this is the error. When we have this here, you will see in a few minutes, and instead of going directly from here to here, then we'll see we have to add one more block here. And you will see that this block that we add here is nothing but a C. Now in this case, X acts directly on the filter, acts directly on the LMS. So now, to generate the signal that goes and update the weights, it requires multiplication of these two signals. Here you will see now I have to make this work with multiplication of the error signal times x operated on it by c. So this times this acts as if I'm taking this signal and I am filtering it again. And that's where the name comes from. I'm taking the X signal and I am filtering it and then sending it to the LMS box. So this part is a filter for the X signal. And we can just say here, a statement here, use LMS if the structural dynamics are not important. And as we've shown that this will work if we have this phase angle relationship. If you have narrow band excitation, this will be valid. If you have broadband excitation and you have 5, 6 modes, definitely as you go from one mode to the other, the phase angle will be changing outside this range and the system can become unstable. So you use this if the structural dynamics are not important or the excitation frequency bandwidth is very narrow. And then of course the XLMS, you use it otherwise. Now we'll write down the error signal. The error signal will equal to Y2 plus D. And Y2 will equal to C times Y1. And Y1, as we got it from before, is X times the weights that we have from the filter. So this will equal to the summation W, I, and K, X minus I. And then we're summing over I from I equals 0 to N. And N is the number of the stations of the FIR filter. Here, a little note here on the side. Transfer functions in the continuous time domain look like this. For example, I'm going to call the transfer function C. And this will equal to numerator, which is function of the Laplace operator, divided by a denominator, function of the Laplace operator. and this C will be C of S. Now if I go in the discrete time domain, I can do the same. In I can write this C of Z, and this will be numerator of Z and denominator of Z. So for example, this can be, for example, Z plus 1, or Z squared plus Z plus 1 divided by something like it, Z squared plus 3Z, for example, plus 5, for example. I can also rewrite this, and instead of Z, I can write it in Z minus 1 polynomials. So if I divide this by Z squared, then this becomes 1, Z to the minus 1, Z to the minus 2, and so on. Why this? Because we can, if I multiply the two sides of the transfer function by the signals that I am sending to this end and this end, then the result will be in terms of the past history. And these things that we can record and keep in memory. Okay? So I can rewrite this as C of Z inverse. Now I have polynomial and another polynomial. I can divide this polynomial and get a result which is an infinite series of Z minus 1 by long division. So by long division I can divide this, and I have the result, for example, 1 plus C1 Z to the minus 1, C2 Z to the minus 2, and so on. And I can keep going until I capture whatever dynamics I'm interested in. And for example, I'll say here, I'll go to C M Z to the minus M. If I go to infinity, then I have the right form. In other words, I can rewrite the C of Z like this. Summation of J from 0 to M. Some constant, C of J, times Z to the minus J. Okay? So the purpose of all this node I can write the system dynamics as some polynomial in Z to the minus 1. Previous samples. Okay. Now the error now will equal to D plus cap C of Z, and I'll leave it for now like what I have here, and then times Y1, which is the summation of I from 0 to M, and then okay, the cap N is again the number of stations of this filter. The cap M, for example, if I have second order system, then I have Z squared, or M will be 2, okay? So the M is the number of order of modes of the system. How high is the order of the system?
Shouldn't M be as large as possible?
Of course, if you,
Not dependent on the system dynamics itself.
of course, like for example, in the Spring MS system, I only put filter 2 stations, but you can run 100 stations.
And,
Yeah, I know. So, you know, like for example, if you have second order system, there is no need to make it very large, okay? But you don't know the system. So you can take this 100, for example. In some experiments on shells, this can go as high as 10,000. Okay, but you don't know. So you start with reasonable number. If you get the system stable, fine. If not, then you just increase this number. If you're interested in the first 4 or 5 modes, don't make this 100 because you'll be wasting a lot of time for the training. So make it as small as possible. You can capture the dynamics that you are interested in. Okay, so now we have the error signal like this. Then the performance index function is error squared. And I'm gonna calculate the weights at station I from the weights of the previous time sample minus the mu partial E by partial Wi. Okay, we don't need this anymore. Okay, so now this is the gradient of the function with respect to the weight. And then mu is again the sample, the step size over the learning rate. Or adaptation rate. Now I want to calculate this number. So now I go in this equation and differentiate it partially with respect to W. The disturbance is independent of the weights. So partially this will go to 0. Then partial E partial Wi will equal to only what we have here. Okay? I'm going to leave this as it is. And then now the only thing that's multiplying Wi is xk of I. So if I select out of these only one specific filter, I, then I will take the xk minus I. So this will be k minus I. Okay. Now this C is not regular C, but it is coefficients times the Z operator inverse. So now I'm going to put it here. But I cannot mix up like what I have here, oranges and apples. This is in the Z domain, this is in the sequence of the time domain. Now we'll go back to what we were talking about. The Z operator inverse means delay by one step. Z to the minus J means delay J steps. So now from here, this will equal to summation. This combined operator will equal to summation. J is equal to 0 to M of the C of J. And then now I have the Z to the minus power J. It means delay what we have here, J steps. So this will be X minus I. I'm going to call this number R because I am summing over the J. So the J will disappear and we'll end up with the K and the I. So I'm going to call this result R K minus I. Now I'm going to take the result, which is this partial, and replace this box. So now the W I K plus 1 W minus 2 mu, and then I need the E, and then I multiply this E times K minus I. So now, if you look at this box now that we have here, this block diagram, I need the E here. But I send at this location multiplication of X and C. Multiplication of X and C. That's this box. I don't send directly X, but I take X, multiply it by coefficients, and delay these X's depending on the order of the coefficients. And that's very similar to what we've done here. Here I send the X, multiply it times some weights, generate the Y signal. So in other words, now I took this X, filter it with the transfer function of the system, and send it in. So now, this transfer function is hardware. This is the system or the structure. Now to implement this controller, I have to take whatever I measure and then do this operation on it. To do this operation, I must know this C. So this C is an identified transfer function of the system. So this is identified structure dynamics. So you have to run some identification to get the C. Now I get the signal and then update it by the coefficients C sub j's, send it to this box along with the E to generate this R, and then the final result will be like what we had before. And I'm going to call all this Q K minus I. And the handout that you had before, you have these diagrams. So this diagram is what we have on the left hand side. So again, the reference input, you filter it by an identified model of the system that has enough of what you want to control. If you have very large excitation bandwidth, you have to have this identification over this bandwidth. Otherwise, you will not be able to match this. Now, from this, you send the signal along with the error signal to the regular LMS, update the weights, generate the control signal to the actuator, send it to the structure that now has important dynamic characteristic, and then generate the counteraction effect that can cancel the effect of the disturbance to minimize the error signal. And this whole thing, now based on the equations that we developed, will look like this. The only difference from this and the regular LMS is this box. Okay? This box is a black box for us. We don't see it because it is a hardware on the structure. We send the actuator to the structure. So this is a black box. Whatever we have on the structure will act upon it by the control signal and then generate the error that we have. This little box has instead the cues that were made from E and X directly. Now it has E, X, and C combined. And the cue that we generate is the E times the R. The R is the C's operating on the X's. Okay? Now we have this modification. Then we will show that this modification, you don't have to worry about the plus and minus 90-degree rule, because it will always be stable operation. It will always be stable operation. If we don't, then we'll show that we can have the instabilities that we've seen with the regular LMS. Okay, just a little note here again. We've seen that the Laplace transform of a signal defined in the time domain is Laplace is equal to this, and this is equal to integral dt. And if we're looking at the Z transform of the time sequence, f of k, then the Z transform of f of k is equal to f of z, and it's equal to summation f of k z to the minus k. I'm going to make equivalence between these two transforms. So we have the function here, and then I have z to the minus k, and k is the sample order. I can write the time t. In general, I can write it as k and t. K is the sample order, t is the sample interval. So to make correspondence between these two transforms, all what I need is to match the operator that I used to make the transform. So I'm going to make e to the minus s t is equal to z to the minus k. To make equivalence between these two. Now the t, I'm going to replace it from what we have here. So this will equal to e to the minus s k and t. And the equivalence, now I can remove the minus k from both sides, and this says z will equal to e to the st. And this is called the exact mapping between the s and z domain. So if I want to look at stability region in the S domain, how would it look in the Z domain? I use this exact mapping. Okay? So and the consequence of this, for example, if I want to map in the frequency domain, I'll replace the S by J omega. So then Z and the frequency domain will equal to exponential J omega T. And if you do this mapping, then you will see this is the S plane, real and imaginary. This is the unstable zone. And I take it and plot it in the Z domain. If S has a real part which is negative, and it starts from 0, then 0 times t is equal to 1. And if the real part goes to minus infinity, then minus infinity times t will go to 0. So the left hand side of the S plane, I can copy it in the Z domain as a unit circle. Anything inside the unit circle will be stable, anything outside the unit circle will be unstable. And this comes from the fact in here. If I have an S which is smaller than 1, then the exponential will drop in magnitude. If it is greater than 1 and the time is increasing, will blow up. So this is stable zone here. This is not important for what I want to do, but anyway, so you can see, if you study digital control, then you will see that the stable zone is bounded inside a unit circle. Okay, but now all what I need is this now. I will see now here the proof of plus and minus 90 degree rule of thumb. And we'll see here now, let the signal x be equal to the real part of some magnitude and phase angle. And I'll just make it J omega T, and then I'll take the T out and replace it by K cap T. So this is in effect, the X is the reference signal, is a cosine omega T signal. Okay, KT is in the digital equivalent of the time small t. Now this is my reference signal. Now I'm going to let the transfer function of the system in the Z domain is equal to some C again, and the time J omega T. And the J omega T, it is minus, because it is C, we had it here, the C is function of the Z inverse operator, okay? And now, just for simplicity, I'm going to say I can reduce all this to magnitude and phase angle. We want to show that the system will be stable if phi is bounded between these two limits, where phi is the phase angle of our structure. And then now z minus I is equal to, from this relationship that we have, is equal to e to the minus j omega t. The I is the delay, so many I steps. So these three things that we will need. Okay, let me begin from here. I want to get del E, del W I for the optimization. Okay, so now del E times del I. I can write it down as from all this differentiation. This will be the C of Z, and then the X is given by this equation. So this is real C of Z, and then X of Z delayed by an I step, so I can write it down as Z to the minus I, X of Z. Then the del W is whatever weight that I want to use. If I use WI, then I am delaying the X by I step, and the I step is right here. Okay, now I'm going to use these relations now to plug in here. So this will equal to the real part. The C is A, e to the j phi. The X is given by what we have here, and it is delayed by an I step. So this will be E minus j omega t and I, and then this will be the e to the j omega k and t. Now I combine all these, so this will equal to A, and then E to the omega k and t minus omega t and I, and then plus phi. Okay. Phi omega t and I, and then j. If I take the real part of all this, so this will equal to A cosine and phi. And this will be the partial, E Wi. Now we want to get the weights. Oops. Then I have to multiply all this times the error, E, and times A, and the cosine omega T and I plus phi. The E I can get it from integrating this equation with respect to Wi, or integrating this equation with respect to Wi, or this last equation with respect to Wi. So this will be nothing but A cosine, same function, times Wi. So this would be my error. This is the partial error by partial W. So now this box is right here, and it is A cosine omega kt plus phi. So if we look at what we have here, then we have A and cosine A squared and then cosine squared. This is definitely positive number. This is definitely positive number. This is definitely positive number. For a given weight that we have here, this number is independent of the phase shift of the plant. The phi is inside, but the phi is here and here. The result is cosine squared. So this will be always positive number, independent of phi, will never change the sign of this block. So the conclusion of all this now, independent of phi, should say the sign is independent of phi. Now let's take another case. For the LMS. The LMS, we said that the C is equal to A e to the J phi. LMS, we said C is equal to 1. So this means that the A is equal to 1 and phi is equal to 1. 1 and 1. So now partial E Wi will equal to, from here, will equal to 1 cosine omega T and I. But my plant that has dynamics will affect the actual error E. And the actual error E will stay as A cosine times Wi. Then Wi k plus 1 minus 2 mu, and then I have two components. The actual error is equal to A cosine plus phi times Wi. Wait a second. Wait, give me a couple minutes. So you can see. Times this partial will equal to cosine T and I. Now I have cosine of two functions. Then I can replace them by cosine the sum plus cosine. So this will equal to cosine phi cosine 2 omega kt minus 2 omega ti plus phi divided by 2 times Wi. From this equation, then Wi, k plus 1, minus 2 mu and A. The first term will be cosine phi over 2 Wi. The second term, 2 mu A. And then we have cosine 2 omega kt minus 2 omega t and I plus phi over 2 times Wi. If you look at this term is time dependent because of the I. I'm sorry, because of the k. Because of the k. The average value of this will go to 0 because it is bounded between plus and minus 1. So the average value will go to 0. Then if I do the averaging, then Wi of k plus 1 will equal to Wi of k minus 2 mu A Wi cosine phi divided by 2. Now the 2 cancel with the 2. Now this result, now if I have LMS controller, the change that will happen based on this box, not this box. This box was independent of phi. It will not change the sign. Now here, if phi is 90 degree or lower, we have one sign. If phi is greater than 90 degree, we have another sign. So the weight can go down or can go up. Can go up and down. So now this can make the system go unstable. The amplitude here is amplitude. Here, amplitude squared. So it depends on how much is the amplitude of the plant dynamics. Is it positive or negative? And how much is the phase angle? Phase angle, if it is bounded between plus and minus 90 degree, then everything will be okay. If not, then the system will be unstable. Now here, then phi, cosine phi will change sign if not bounded by plus or minus 90 degree. Yes, sir, Muhammad, your question.
I just wanted to note that phi for the LMS is 0, not 1. That's all.
Now, yeah, see here, this is for LMS. I put the fee is 0.
So, yeah, it's written one of it. That's all.
Oh, I'm sorry. Yeah, should be 0. Yeah. So there is no phase angle, and the amplitude is unity, and we're pushing through unity. So now this is the rule for changing the weights. But I have to use the actual error in my calculation of the weight, because this is what I'm measuring by the sensor. So it has the plant dynamics. If I use the wrong algorithm, then it means that I'm using the wrong partial derivative. And when I do, then the result will be dependent on the phase angle of the system. If it is not bounded between this, then the sign will change, and the gradient search will zigzag, will never go monotonically to reach stable limit. It's fantastic. We have 5 minutes, so we'll not be able to see the lab, but come in the lab anyway. You can see what we have, and then we'll run a very nice experiment on Wednesday. This will be on LMS. So you just see it now working, so you can see it works, and then we'll show you the details next time. Using the transpose of one and the other. And we showed that this system is robust, and it has infinite gain margin and phase margin greater than 60 degrees. Once we put the LQG, then we lose robustness. And to regain this robustness, we looked at the design of LQG/LTR, which is the loop transfer recovery. And the loop transfer recovery is just approach to gain the lost robustness of the LQGR. So the LQG due to the use of the Kalman filter. And then after we finished this, I did the norms. We did the H2 norm. And the H infinity norm. We did the H infinity norm by the singular value decomposition, the frequency response, and MATLAB, and finally we've done it by the Hamiltonian matrices. And here primarily was MATLAB, which is implementation of the controllability and observability. And we had the H2 norm of any transfer function is equal to the square root of the trace D transpose DMP, which W0 is the observability gradient. first to minimize the infinite node G, and G is the transfer function between input disturbance and the output measurements that we have. So this is the G is the transfer function of the output and input disturbance. And then we selected Z to be special form so we can capture the dynamics of the structure as well as the controller energy. So this is some desired output parameter. I'm sorry, undesired. I have to minimize it. And then W is the disturbance. We designed this also by looking at the controller first and applying the Hamiltonian matrices. And then we repeated the same thing that we've done with the LQG, using the separation and duality principle for designing the Kalman filter. Again, using the dual Hamiltonian matrices. After we finish this, we start putting weights on the parameters that we want to eliminate or minimize, and these weights, we put them in the presence of uncertainty. Okay. So we use weighing transfer functions. To shape the desired output according to the uncertainty and the disturbance profile. To shape the output. Let me erase the first part here. Shape the output according to the disturbance, measurement noise, and uncertainty. And we use MATLAB with the command H infinity synthesis, so we can synthesize the control of the system, which is a combination of these two. So we synthesize the controller, which is, again, this is the plant, this is the Z, this is the W, then now this is the output, and we combine everything in one box to give the U. So we use the H infinity synthesis to calculate this K. Then we did the small test using the small gain theorem. To ensure system stability. And we found that the T and and delta should be less than unity, or we can put and T is the closed loop transfer function of the system. Which is, we call it the consensitivity transfer function. The last part that we done is the feed forward. And here we've done three things: the LMS, the FXLMS, and then the last thing that we've done last lecture was to look at the very important rule of thumb, which is the plus or minus 90 degree phase shift. We covered a lot of ground. I wanted to cover more, but it's almost impossible, physically impossible. So I hope we done some justice in this. This class was all pure control theory, because that's what I'm lacking in the book, so that's why I wanted to stress it. So I still owe you some sections from here. Unfortunately, you would pay for them when you buy the book. Okay, so I am hoping I can finish by end of the summer. So you've seen the implementation of the LMS on DSpace, and if I were you, like invest a lot of time on DSpace, because that's the very important approach, and it's very common and very popular in all the vibration and noise control community. So the DSpace, because it links very easily with Simulink, it makes life very easy in implementing the controller. So that's what we've done. I had great time in the class, despite of the energy level that required, but nonetheless, so it's thank God it's over. So on Friday, please, if you have time, please come and pick the homeworks, and then we will not have final exam. And I will see you next semester. Next semester I'm not teaching, thank God. So yeah, so maybe in the fall. We'll see you in the fall. Thanks again. I will see you guys later.